In the world of construction, straight is the ultimate law. If your foundation is off by some centimeters, your roof is a disaster. But at the scale of the Burj Khalifa, the world's tallest structure, vertical becomes a moving target. If the base of the building is off by just a fraction of a degree, by the time you reach the top, you are not looking at a skyscraper. You are looking at a $1.5 billion leaning Tower of Pisa. So, why did the surveyors of this project intentionally build it crooked? Why did they spend 6 years steering this tower into a curve that wasn't on any of the original blueprints? The answer involves space-age satellites and a secret that changed the way we build forever. Hello, I'm Daniel Oinaina, and today we are talking about the invisible pirates of the construction world, the surveyors, and specifically how they managed to steer 500,000 tons of concrete over 800 meters into the sky without ever losing their way. Most of us think of skyscrapers as these rigid, immovable objects. But the Burj Khalifa, due to its enormous height, it's not static. And most of you, at one point in time, build something. Maybe a dog pen or a small structure. And the challenge factor is keeping the structure vertical and level. This is why during construction, engineers and surveyors work together to ensure these factors are met with high accuracy. Building the Burj Khalifa was something historic, and every time with marking events, I've observed and they do not come easy, especially true for the surveyors handling this mammoth of a task. When a building is being set up, you have seen surveyors looking through different instruments, a theodolite or even a level machine. These are the standard for setting out, and they were applied immensely until the project reached the 20th level. At this point, resection from control points on the ground became impossible and difficult. And the reality of the higher you build, the harder it becomes, started to set in. At this level, the challenges joined hands. First, you have strong winds, which are not a breeze anymore. Second, the desert climate is causing the side exposed to the sun longer to expand. And also, since there is no stable ground, as you increase the weight, the raft foundation will start to settle and sink. So, if the building is leaning, swaying, and sinking all at once, how do you find true north? Or even just straight up? To build the world's tallest building, surveyors had to invent a way of finding a fixed point in the middle of a moving sky. They couldn't look down at the ground anymore. So they started looking up at the stars, or more accurately, the satellites. That means they needed a new way to do the work. To solve this, the team at CWCSS and the project surveyors developed what they called the Core Wall Control Survey System, or CWCSS. They installed 3 high-precision GNSS, or GPS, antennas on the very top of the building's active formwork. But the problem, standard GPS is only accurate to a few centimeters. In a skyscraper, a few centimeters is a disaster. So how was this problem fixed? They used differential GPS and one total station. They had a base station on the ground at a known point, By comparing the signals between the ground station and the roving antennas on the roof, they could cancel out atmospheric errors and get their position down to a much higher degree of accuracy. But here is the real genius of the system. You see, a total station normally relies on an internal compensator to find level. But on a swaying tower, gravity is a liar. If the building is leaning 100 millimeters to the west, the instrument sitting on the 100th floor thinks down is rightly tilted. Its vertical is no longer the same as the world's vertical. To fix this, the team used 3D transformation as a bridge. They were essentially managing two different worlds: the rock construction grid, which is how the building sees itself, or what was measured by the total station, and the global coordinate system, which is how the rest of the planet sees the building, which was what was measured by the GPS. By using real-time least squares adjustment, the computer would take the distorted geometry seen by the total station and mathematically snap it back into the global map provided by the GPS. This allowed the surveyors to subtract the sway and the lean in real time. It gave them a clear, stabilized picture of exactly where the building's skeleton was headed, which now allowed them to do surgical adjustments on the subsequent floors. But even with GPS, there is a catch. GPS tells you where the antenna is, but it doesn't tell you if the building is raining. If the wind pushes the tower, the GPS might show the right coordinate, but the building's spine is actually curved. This is where the inclinometers come in. Think of this as the building's inner ears. They are incredibly sensitive electronic levels placed throughout the core of the tower, and they are placed at an interval of 8 inclinometers per every 20 floors, and they measure the tiny fractions of a degree that the building tilts due to wind or sun. The survey team took the position data from the GPS and fused it with the tilt data from the inclinometers. By running this through a computer model in real time, they could calculate the true vertical, which is the theoretical center of the building. Even with all that tech, the most important tool was the clock. Because of the high temperatures, the sun was stretching the concrete, which means the building was most relaxed and vertical in the middle of the night. This made the survey team to perform their most critical setups between midnight and dawn. They would take the high-tech data and verify it when the building was at its relaxed state. Then mark the exact point where the next day concrete would be poured. At this point, you might think the surveyor's job is just to tell the construction crew exactly where center is so they can stay on track. But in reality, if you build a mega tall skyscraper perfectly centered on each and every day, you will end up with a building that is permanently leaning. This brings us to one of the most fascinating parts of the Burj Khalifa's story: precompensation. Every time you add a floor to a building this heavy, the layers of the concrete below compresses. It's like sitting on a very tall stack of sponge. But here is the tricky part: the building doesn't compress evenly. because of the way the weight is distributed and the slight variations in the soil. One side might sink 10 millimeters more than the other. So the surveyors would take this data and analyze it. And if the building was starting to sink more on the north side, they would take action and tell the former crews to offset the next floor. If the building was predicted to lean 20 millimeters to the west due to the weight, then the surveyors would steer the construction 20 millimeters to the east. They were essentially building a slight curve in the structure, knowing that the weight of the future floors would eventually squeeze that curve back into a perfect straight line. It's like aiming an arrow slightly above the target to compensate for gravity. In the surveying world, we call this vertical alignment control. It's a constant game of chess between measured gravity of today and the predicted weight of tomorrow. This is why surveying is so much more than just looking through a telescope. It's a mix of legal precision, structural engineering, and a bit of fortune telling. The surveyors on the Burj Khalifa had to process thousands of data points from the GPS, the inclinometers, and settlement sensors, which they would then decide where the center should be on any given Tuesday. The Burj Khalifa is often called a triumph of architecture or a miracle of structural engineering, and it is. But look closer at those 828 meters of steel and glass. And what you are really seeing is the world's tallest monument of measurement. Before the first shovel hit the dirt, a surveyor had to define exactly where that dirt was. And every day for 6 years, as the tower rose into the clouds, it was the surveyors who held the line. They turned a point in space into a physical reality. If you are a surveyor, an engineer, I'd love to hear about the most challenging points you ever had to find. Leave a comment below, and if you enjoyed this episode, hit the like button and subscribe for more content of this nature. As always, thanks for watching. See you on the next one.